the Vinogradov mean value theorem. Well, first, the Vinogradov mean value is obtained as the following average over the the k-dimensional interval 0, 1. You can look at it as k-dimensional torus. So you have the 2s power of this trigonometric polynomial here on the k torus. So you have x1, x2, xk are in 0, 1. And then you have a summation here over n with the frequency n square, etc., n to the k. So the integral which is here, of course, has also an arithmetical meaning, because what you're counting is the number of integer solutions to the system of k equations, which the system in the variables n1, n2, n2s, which are obtained by letting j here run from 1 up to k. So clearly, if you just look at the diagonal contribution, you see that this quantity here, which I call the Vinogradov mean value, is going to be at least n at the power s. So this n at the power s is certainly a lower bound, comes from the diagonal contribution. And well, if you're looking at the contribution of, say, the major arc around 0, which means that you are cancelling all the oscillations. So you will take x1, say, less than 1 over n, x2 less than 1 over n square, xk less than 1 over n at the power k, then you don't have oscillation. Then you see that you also get a lower bound on this mean value, which is going to be n at the power the number of variables, which is 2s, minus 1 plus 2 plus 3 up to k, which is a half. I have to get used to this thing. Which is a half k plus 1. So the expression which is here is certainly a lower bound for jskn. So what Wooley calls the main conjecture is that, in fact, this jskn is exactly of this order up to, let's say, a factor n to the epsilon. So we can start talking about this n to the epsilon, but I will not do that. For me, it just means that you can take here an epsilon which is arbitrarily small, and with the usual notation here. So we are not going to get into the, in particular, the role of k. So for me, the k is going to be fixed. What's quite interesting is to understand also what is the role of k, but we are not going to do that. So this problem is non-trivial. So I will call the reason why it's non-trivial is that in some sense until 2014 it was only proven for k equals 2. So the exponent k plus 1 is called the critical exponent because this, if you take s to be k plus 1 over 2, then these two terms are the same. Are of well, like it's written here, they are the same. So in other words, the diagonal contribution is the same as the other contribution which comes from the 0 major arc. So what did Vinogradov prove? May be stated in the following form. So that goes back to 1935, and then whatever is written here are later improvements which are due to Karatsuba and Stechkin. He proved that this inequality holds in what you may call a supercritical regime, where you take s significantly bigger than k plus 1. So what you see here is that it should be bigger, say, basically by a factor log k. So at that moment, of course, the main term is going to be the second term here. You will get the statement which is written here. jskn, etc., behaves like that, and this csk can be analyzed more specifically and is important in certain applications. Now, there is a very important progress which was made in the recent years by Wooley. Roughly speaking, what he succeeded in doing is removing this logarithm of k. So what did Wooley do? First of all, Wooley managed to prove this main conjecture when k is equal to 3, which is certainly a very significant achievement. What he also proved is that the conjecture is true. So when you go to the supercritical regime, meaning that the second term is going to be the dominating term here, if S is at least equal to k minus 1, so as you see, this is still off from the k plus 1 over 2, basically by a factor 2. And then in the subcritical regime, when you take smaller s, well, as you see, he's getting very close to the critical exponent there. You get k plus 1 over 2, but still there is a loss of some multiple of k, basically. So in some sense, the results of Wooley, they are based on quite different techniques from what I'm going to use here, at least superficially speaking. They are coming quite close to whatever we want to prove here. So it turns out that actually this Vinogradov mean value problem turns out to be an analysis statement, as I will explain you in a moment. Unlike certain other bounds, for instance, if you take an estimate like Huas lemma, what is called Huas lemma, is an arithmetical statement. But this statement, this Vinogradov statement, turns out to be an analysis statement. And so this was proven in joint work, so we get basically the result in the full strength, which was stated there as main conjecture. This is a joint work with Cyprian Demeter and Larry Guth. Now, just to say a few things before I will try at least to get some ideas of the proof. What these things are good for? Well, classical applications are the Waring problem, bounds on Weil sums, and also zero-free regions for the Riemann zeta function. Now, it turns out that for this last application, you really have to take k very large. In fact, k is going to be comparable to some power of the logarithm of n. From that respect, neither Wooley's technique nor, well, we didn't really analyze it very carefully, but it certainly doesn't look like also the methods we are using are very good. So in terms of understanding the behavior for large k, basically still the old techniques a la Vinogradov, they seem to do the best so far and leads to the best known results for zero-free regions of the Riemann zeta function. So I will not go on that. On the other hand, we are getting quite significant consequences for the Waring problem and also for bounds on Weil sums. So let me just quickly tell you what are implications for the Waring problem. Well, there are, talk about the Waring problem, there is the little g, the capital G, and what they call the capital G twiddle. So I will only, the little gk means that you can write every integer n as a sum of little gk, kth powers. The capital Gk means that it's true provided n is sufficiently large. And then the g twiddle is the least number you need, not just to have a representation, but to have the expected number of representations. So the expected number of representations of n as a sum of s kth powers, roughly speaking, if you take s sufficiently large, should be like n at the power s over k, because s is the number of variables, minus 1, just from distributional considerations. The asymptotic formula is an expression where you will have a main term which is obtained as a product of local densities. So the n s over k minus 1 is basically the Archimedean density we're just talking about. And then the sigma skn, which is called the singular series, is just the product of the p-adic densities. So that is the main term, and then what we want is an error term which is going to be small compared, at least compared with the n s over k minus 1. So that is what we call an asymptotic formula. And then the question is, how large do we have to take s? And the g twiddle k is going to be the smallest s for which such a formula can be obtained. So, in fact, Wooley worked out the consequences of the main conjecture to the asymptotic formula. What is the role of the main conjecture? Well, if you're familiar with the Hardy-Littlewood circle method, you have major arcs. And major arcs basically give you the piece. It gets you the piece, the first term, which is the product there of the densities.
Yeah, use a stick.
I think I will use a stick because this is not very. Ah, where is the stick?
Used to be one.
Ah, there it is. Okay, thank you so much. So, like I said, the major arcs, they give you a thing like that, and then you have some sense, most of the non-trivial work is to control what happens on the minor arcs. So there is a technique, in some sense, to exploit this Vinogradov mean value to get good bounds on the minor arcs. This is a non-trivial analysis, which has been refined by Wooley in particular in function of his results and then with certain conclusions. And the same paper also gets you whatever comes out of this method, assuming that you would have the full Vinogradov main conjecture. So you get a bound there for G twiddle k, which I'm not going to read. It's written there. In particular, the G twiddle 4 you get is 15. I think what was known is 16. Then the G twiddle k for k equals 5, you would get a bound by 23, while before the best which was known was due to Wooley 28, etc. And actually you get an improvement of all these G twiddle k's except for k equals 3, which is an old result of Vaughan from 1986. So as a measure of comparison, what Wooley got with his results on the Vinogradov mean value theorem was an estimate like that, but with an extra factor here is a little bit, say, slightly worse, and you get 1.5 or something like that. And so that already led you to improvements of G twiddle k for all k, which was, I think, was at least equal to 7 or something like that. But that thing gets you every improvements for all k except for k equals 3. Now, val sum, so recall that the fkxn is that exponential sum. So now we are not going to take an average. We're just trying to get a pointwise bound. So what you have written here is the well-known inequality of Hermann-Weyl. So you have the quantity which is written here, which is raised at the power 1 over 2 at the power k minus 1. Well, of course, when k is large, this exponent becomes very small. So Vinogradov methods allow you to do better. So there is, again, a way of exploiting this average information for a large power, this Vinogradov mean value. And so this exponent 1 over 2 to the power k minus 1 can be lowered significantly, can be lowered to 1 over k at some power. This is what Vinogradov did. And then Wooley, with his results, got 1 over 2 k minus 1, k minus 2. And with the optimal VMT, you get 1 over k minus 1. Note that this statement is a little bit more general than Weil, because you make an assumption here, not necessarily for the last one, xk, but you can take an intermediate one, say j between 2 and k. You make a Diophantine assumption like that, and what you're going to get is a bound, which is the one written here, which differs from this one in the sense that you have to replace the k here by j. Of course, the power here is getting 1 over k minus 1. So these are, so again, this estimate is better than Weil, and also better than improvements of Weil that has been obtained later, in particular. What?
Sigma k or sigma k is smaller than the Wooley bond. Is there a factor of 2?
No, sigma k has to be has to be bigger, right? The bigger the better.
If it's bigger, it's better.
Yeah, the bigger the better. So sigma k, this one is bigger than that, right?
There's a smaller, bigger.
No, here there is factor 2. Well, okay, for larger k, right, is better. Okay. In any case, this thing is only useful for k at least equal to 7. So for k at least equal to 7, it gets an improvement of Weil, but also of later refinements of Weil. In particular, there is work by Hees-Brown. I guess still has the best bound for k equals 6. And then there are other papers by Robert and Sargos, for instance, etc. And, well, what it turns out is that that gets you the best for k at least equal to 7. Now, let me talk a little bit about the proof. Proof altogether, like I said, is an analysis statement. Conceptually, it's not extremely complicated, let's put it like that. But, well, I mean, not extremely complicated, and based on ideas which were around. At some point, I will still have to introduce some terminology to explain what is going on, just to avoid having to rewrite quite ugly expressions. So first of all, what is the analysis generalization? So taking the moment curve, so instead of taking something discrete, we have something continuous here. And you can take t between 1/2 and 1, for instance, doesn't matter, you can always rescale. Moment curve is not absolutely essential. Basically, what I'm using is that the curve is non-degenerate. And then what you can do is define an extension operator. So what we are doing is so you take a function g, a complex function 0, 1, and you restrict this function g, say, to an interval j in 0, 1. Then the ejg of x is defined that way. So what is really, what you can do is use g to introduce a density on gamma, and you restrict to j, which, if you want, gets you an arc on gamma, and then you're just looking at the Fourier transform of that. So it's basically a Fourier transform of a density that lives on a curve. Now, there is something technical, but it's important when you want to write the proof of the proof correctly in some sense, but for our discussion, I will omit it. So I will consider moment inequalities on balls. In fact, one cannot quite use balls, but one should use certain weight functions, which have the same shape as a given ball, but decay at infinity. Because there are certain certain points there are issues of positivity of the Fourier transform and things like that. But or you want to have a Fourier transform which is supported by a bounded region or something like that. Let's just drop this thing later on because basically this is just a sketch of the main ideas and identify. So usually I will identify WB with the actual ball. So what we want are moment inequalities. And the statement we're proving is here. So you have a delta, you take a small delta, and then you break 0, 1 up in intervals of size delta. So what you can do is try to compare the E01G with the components EJG. So the E01G is just the sum of the EJG. You expect a certain kind of orthogonality there. This is very rough. Anyway, the bottom line is that you can bound, now you have to be careful, the dd plus 1 moment with respect to this density by the L2 function of the corresponding dd plus 1 moments of these components EJG up to a factor delta minus epsilon, but it's quite important how large you choose this ball. So this ball has to be of a radius, the radius r here, has to be at least delta minus d. That's quite important. Now, of course, you can ask me, you would have this inequality trivially say in L2, what happens for intermediate values. This inequality also holds for moments which are less than dd plus 1, but this is not trivially by interpolation. It follows basically from the proof. I didn't state it like that because that is all I care about in some sense for what I'm going to do. Now, so clearly this is an analysis statement. The result which is stated here for d equals 2 was already obtained in a paper, an earlier paper which just appeared with Demeter, and that implies you the well-known result of Vinogradov mean value for k. Yeah, the d which is here is the k from what I was talking about before. The Vinogradov mean value for k equals 2. And this is also where we observed that somehow, realized that it was possible to get really arithmetical statements from analysis just without using divisor functions or things like that. And then it became quite attractive in some sense to try to get everything again using decoupling. This is what you call a decoupling inequality. So there are many such decoupling inequalities. This is a decoupling inequality for curves. So we had the decoupling inequalities for curves, but they were not quite as strong as the one which is written here.
Epsilon is not coming from the
No, it comes absolutely not. It comes from things which we didn't do too carefully and presumably are necessary. In that statement, you cannot avoid a delta minus epsilon. What is possible is that in the subcritical regime you can eliminate it, but definitely we don't know how to do that.
Why is it called decoupling?
Well, because you basically decouple, because you decouple the E01G in these smaller pieces EJG. So, right. So we call it L2 decoupling because there is an L2 here. In certain cases, the L2 gets replaced by something else with inequalities which are still morally of the same value. For instance, you have decoupling inequalities for hypersurfaces and things like that, which are interesting for PDEs. In fact, I spoke about that at an earlier time. But here we're talking about curves, and so that is the statement we can get. So what is the relation to VMT? Well, what you do, first of all, you can discretize that because your GT, you can take small intervals around points and then passing to the discrete. So the inequality which is here is just a reformulation of what I had before. which is that. So if you take p to be dd plus 1, so that term will disappear. You get your n to the epsilon. So what is written here is, so the r here is going to be 1 over delta to the power d. So the delta, it's 1 over n, of course, and then the r has to be bigger than n to the power d. So for p equals dd plus 1, this is just the previous statement. Now, I wrote the statement for a general p. Why can you do that? Well, in that case, interpolation is trivial. It's just Hölder's inequality. So you get it for p equals 2, of course. Without that, it's just orthogonality. And then by Hölder, you will get it for p between 2 and dd plus 1. And then what happens on the other side, you're going to get that term using interpolation till infinity. Now, in that form, it is clear that you get the VMT because, well, what does it mean? This is just counting. So you have these Tn's, which are points between n minus 1 over capital N and n over capital N, arbitrarily chosen. What you're counting is a number of solutions of that system. When you look what this thing really means, what you're getting is the statement which is here, because a ball r is of, so you take a ball r, say, of radius n at the power minus d. So you get a bound on the number of solutions, so the little a-n's are equal to 1, with the quantity that appeared in the Vinogradov mean value. Clearly, you get something which is smaller if you would put equals 0 here. If you take Tn equals n over n, that will give you exactly the statement which was earlier, namely that the number of solutions of that system here is going to be bounded by what is there. Note that, in fact, just for the side comment, if you take Tn to be n over capital N, then the system of inequalities you have there, of course, is the same as what you would have with the things being equal to 0, just because an integer which is less than 1 is necessarily going to be 0. So, like I said, the proof is not extremely complicated. So what I want to do is try to give you, is at least conceptual, not extremely complicated. Trying to tell you a few of these ingredients, which are what you may call, say, ingredients of, say, modern harmonic analysis, whatever this means. So first of all, there is something called wave packet decompositions. So what is the idea of that? Is that you will take a small arc on that curve, and then, so the EJJ is the Fourier transform of that arc, and you look at the modulus of that. So basically, this modulus is going to be a function. This is not quite correct, of course, but this can be made rigorous. It's going to be essentially correct on boxes, which are going to be, so in the plane, it would just be 1 over delta. So the boxes are just the polar of the arc, right? So it would be 1 over delta square, and when you go in higher dimension, remember, well, you have a non-degenerate curve here, is that you're going to have a box which is going to look like that, and the basis, this box, is just oriented according to the usual Frenet basis. So it's not true that this Fourier transform has a modulus which is essentially constant on such boxes, but that is more or less the heuristic. Then there is something which is very powerful, which is what they call parabolic rescaling. So essentially, you want to go, if you have a small arc, you want to say something about the small arc by going to the full arc in some sense. So for d equals 2, for instance, let's say that we're looking at a sub-interval T0 plus sigma, where sigma would be rather small. So we take a T of the form T0 plus sigma T prime. And then we are writing, so we take d equals 2, x1t plus x2t square. So it's clear that you get the expression which is here. So it's also clear that you're making a change of variable. So you have to make a change of variable then. x1 prime would be sigma x1 plus 2, 0, x2, and x2 prime is sigma square x2. So assume that x1, x2 is sitting in a ball of radius m, say. These radii are quite important. What's going to happen is that the map x1, x2 going to x1 prime, x2 prime is going to give you an image which is going to be some kind of elongated ellipse. But this ellipse is still, I don't know how you call this, going to have, I think you call this injectivity radius, right? Which is going to be sigma square m. So basically it is obtained from balls of radius sigma square m. And in general, what's going to happen is that you get balls of size sigma to the power dm. Now, why do I tell you this story? Well, the reason is the following. We are trying to prove these decoupling inequalities. So really like to bound that by that, say with a delta minus epsilon, at least for certain p's. Well, let's write here a constant kp delta. So kp, I shouldn't call it a constant, a function of delta, kp delta, right? Then the point, of course, that we like to bound kp delta. So, so what we like to prove is that when p is equal to dd plus 1, kp delta is delta minus epsilon. Like I said, you have it for all p, but it's not just interpolation. Any case, what follows from parabolic rescaling is the following. Assume here that I will restrict my function g to an interval j0 which is of certain size sigma. Sigma bigger than delta, sigma is small. What happens from parabolic rescaling is that whatever the function kp delta you have here, if I take a g which is supported by such an interval j0, the kp delta can be replaced by kp delta over sigma. So delta over sigma is going to be bigger than delta. So of course, the idea is that the kp delta is going to increase with decreasing delta, right? So there is a certain saving there. So that is something which is essential in the argument. Now, what is used a lot are techniques of transversality. So let me just give you the simplest possible case. Say, let's say we take d equals 2. Let's say we have two intervals, j1 and j2. We take order 1 intervals. We take delta intervals. We take delta intervals which are going to be O1 separated. So then we can look at the extensions ej1g and ej2g. So when you think about it from the wave packet decompositions, these moduli, they are basically constant on boxes which are kind of transversal. And so that gives you a certain independence, which allows you to claim that, so you take here a ball, say, which is of radius delta minus 2. The LP norm, the average LP norm on that ball of the geometric mean can be obtained. So what would be trivial from Hölder is to bound it by the geometric mean of the LP, of the average LP norms of the factors. But it turns out that, in fact, you can do it with p over 2 because, in some sense, these two things, they behave independently. You have a similar statement in higher dimension, and you have more elaborated transversality statements, which I will not recall to you now. So they are using this wave packet decomposition I described earlier, and then basically they are derived then from Braskamp-Leap, from a Braskamp-Leap inequality, which maybe I will state later, and further developments of these Braskamp-Leap inequalities, which are called multilinear Kakeya estimates. So all these things were developed, say, so these multilinear Kakeya estimates, they go back to a paper of Bennett, Carberry, and Tao, I don't know, say maybe 6 years ago or something like that. So I really want to exploit very much multilinearity, but I have a linear problem. So there is another important trick here. It's how do you go from linear problems to multilinear problems. So the way to do that is the following. So you have 0, 1, and let's say we break it up in intervals, disjoint intervals j1 up to j capital A, where capital A is going to be quite large. You can think of it as constant, but a large constant. So then, obviously, you have a bound of absolute value of E01j by the sum of the absolute values of the components. So what I'm doing here is something which is basically completely trivial. Essentially, what I'm saying is that there are two possibilities. In this sum, either you have basically only one term which contributes, or 2 or 3 or whatever, 10 consecutive terms which contribute. In that case, what you can do is bound that by the second term here. Or you have more terms that have a significant contribution. In that case, what you can do is bound it by a bilinear expression with two intervals, js and js prime, which are separated, say at least 10 over a separated, and with a constant here depending on a. I don't care about the constant depending on a here because I have my bilinear estimate and then I can work with that. The important thing is that what is here does not, the constant which is here does not depend on a. Because remember that, so that gets you a bound like that. Remember that from the parabolic rescaling, the contribution of the js, which are 1 over a of the full size, is expected to come with a saving due to this 1 over a, which is going to be, say, some power of 1 over a. So you gain something which is like a power of 1 over a, but you only lose a fixed factor here. So this thing can then reprocessed. You can rescale gs to something larger. You can re-subdivide and keep going like that. And so every time you're going to gain on the size a factor 1 over a, and you only pay a price which is like a constant here. So that is the idea of this multilinear reduction, which has been used before and is the main step to move from the linear problem to multilinear expressions. So like I said, I will have to introduce some notation. What I will do is the following. So the geometric average here, I going from 1 up to m to the power 1 over m, this is what I called the multilinear reduction. So this capital M is going to depend on d. For instance, for d equals 2, the capital M will just be equal to 2. And then what we have here are these L2 functions, so like I described before, where these L2 functions are taken for a subdivision of intervals of size delta 1 in intervals, say, J1, J2, Gm. So J1, J2, Gm in 0, 1 are intervals which are fixed. They are, say, order 1, and they are also order 1 separated in order to have the transversality effect. And the delta is a ball of a certain radius, say a radius m, where m is always going to be assumed to be larger than 1 over delta 1, and sometimes considerably larger. So I have this expression, and I also want the following expression. So here I will consider a very large ball, which is basically the ball I'm getting in the decoupling inequality. And what I will do is take the LP average of these expressions I defined before, where now the capital delta ranges over, say you can take a cover, whatever, ranges over the m balls contained in B. Note that we have a Q which is at most equal to P, and that here the P, the P is going to be basically, the P is going to be fixed So in some sense, I'm going to play with these quantities. And, well, first of all, observe that the LP, so what you like to do is bound. The decoupling statement I made was in the decoupling theorem was bounding the E01G in LP, average, take the average LP here, by the quantity dPb delta. dPb delta, which is the one which appears here, where the delta 1 is going to be delta and the capital delta is going to be the whole ball, so there is no averaging anymore. So what I want to do, the goal, I mean, a way to restate the decoupling inequality is to say that this guy, say for p equals, say, dd plus 1 or smaller, is going to be bounded by that up to a factor delta minus epsilon. So what will be done is to move gradually towards this quantity by decreasing delta 1. So we will start from some delta 1 and then we'll try to decrease delta 1 and increasing the size of the ball. So the decreasing of delta 1 will be achieved by lower dimensional decouplings, and the increase of m is going to be obtained by exploiting transversality. Well, restating the statement I wrote you before, which is the statement. Let's see, where did I write it? I wrote it somewhere. Yeah, restating what I put down here. When you go to smaller intervals, leads to the statement which is here. Because what you have here is a decoupling in arcs of size delta 1, and then in order to get arcs of size delta, you do a further decoupling with an extra factor which is delta over delta 1, and the price you pay for it, it's the Kp of delta over delta 1. Now, talking about decoupling, of course, the simplest decoupling is just using orthogonality, and this is for p equals 2. So what you see in particular is that if we have a delta 1 which is at least equal to 1 over m, so these are arcs here of size delta 1, but because of orthogonality, you can further reduce them to arcs of size 1 over m. This is in fact a place where you can't quite use a ball, you have to smoothen it a little bit. So why is that true? If you go back to the definition, if I take here my q equals 2, okay, the capital delta here is a ball of radius m. Here I have something, the extension for an interval of size delta 1. What you can do by orthogonality is break this thing further up, in fact, in sub-arcs, sub-intervals, which are of size 1 over m, basically. So this is, if you want, it's the simplest decoupling. Then there is a statement here that's one more thing I'm going to use a lot, which I call interpolation. It's just an application of Hölder's inequality. Is that when you have a q between two exponents, q1 and q2, then you have the usual interpolation formula with the weights. Now let me give you an idea of the proof for d equals 2. So what we will start with is a scale delta 0, which is a small power of delta, so delta 2 minus u, say, where u is, say, a fixed large constant, and basically you have the epsilon in the statement. When you want to make the epsilon small, you will have to take this u appropriately large. So what you have here is just a completely trivial statement. This is just from the triangle inequality, where you decouple on arcs, say, which are of size delta 0. And what I will consider is the bilinear version of it, where I make a geometric average over two intervals, say J1, J2, and 0, 1, which are 1 separated. So what I'm getting here is in fact the expression d2 delta, capital delta, delta 0, where capital delta is the ball centered at x of radius 1 over delta 0, simply because I can bound pointwise, I can bound this thing here by the average L2 norm on a ball here, which is, because the I is of length delta 0, I can take a ball of size 1 over delta 0. So I get the delta 0 minus a half, and then I get d2 delta delta 0, fine. So the delta there, basically what we are getting here is d2 twiddle delta 0 minus 1 delta 0 by taking an average over the ball's delta of size 1 over delta 0 and the big ball B. So we're getting that with an extra factor delta 0 minus a half. So we need to bound that. And so, like I said, what we like to do is to increase, well, we like to decrease delta 0, the size of the arcs, and increase the size of the ball. So there is a first obvious thing. We take p, say, less than 6, near 6. In particular, p is larger than 4. So p over 2 is at least equal to 2. So just trivially, this guy is going to be bigger than at least equal to that. But the interest of the p over 2 is that I can use my transversality I mentioned before and do a ball inflation. So remember that we are looking at an average of balls of radius 1 over delta 0 in the big ball. So what we can do is first take an average over 1 over delta 0 balls taken in a ball of radius 1 over delta 0 square, and then take an average of 1 over delta 0 square balls in the big ball. So it turns out the first average can be moved inside because of this transversality in order to get that. So what I'm saying here is just a reformulation of this inequality here. There's nothing more to it. It's just follows from that here. So what I have achieved here is what you may call a ball inflation, because I replace a ball of size delta 0 minus 1 to a ball of size delta 0 minus 2. Now, once I'm here, I'm going to interpolate. I interpolate p over 2 between 2 and p, so you get exponents 1 minus theta and theta. The important thing is that theta is less than a half for p less than 6. This is somehow why 6 is going to be the critical, the endpoint there is that the t is going to be less than a half for p less than 6, and somehow you will see why that is important, that theta is less than a half. So you have just the interpolation here, but now because this is 2, you can do just the decoupling by orthogonality. Since I have a ball here of radius 1 over delta 0 square, you can by orthogonality decouple, in fact, in intervals which are of size delta 0 square. So what happened here is that I moved from here to there, and what I saved basically, what happened is that the delta 0 goes over in a delta 0 square. I get an exponent 1 minus theta, and I get a second factor here where I can't do anything anymore, which is the dp twiddle. So this is what we're getting, what I just mentioned to you before. So then the natural thing is to iterate that. So you iterate with an r which is going to be significantly smaller than this u I gave you in the beginning. So this iteration is completely straightforward. You just write what it means. You get that. And then, we have to estimate dp b delta 0 2 to the power r, because what we really need is dp b delta. So what we do is, using this inequality which I mentioned to you, which is the one which is here, which allows you to go from a delta 1 to a smaller delta with a certain loss, the kp being these factors which were defined before. So the point is that what matters is that you evaluate kp for the ratio between delta and delta 1. So you apply that, and what you're going to get is the ratio between delta and delta 0, 2 minus r. So you're going to have these kp's. In fact, here I could have just written kp delta. I'm not even going to use them. And so remember that there is an extra delta 0 minus a half in front. At the end of the day, what you obtain is some kind of inequality like that, which is just reformulating what is here. So this is purely formal. No, I will do something which is not completely clean, but just to go fast. Let's write kp delta, say, as 1 over delta to the power gamma. What we like to show is that basically gamma is very small. So if we rewrite the statement which is here with the kp delta, which is delta to the power gamma, what we see is that we get this inequality here. It's just reformulating what was before. And now what you see is that you have a gamma on the left, and then you have gamma 1 minus theta to the power r from here, and then the sum, gamma, the sum is going from 1 up to r, theta 1 minus theta is minus 1 from the second term here. So this plus that is also gamma. So in other words, this gamma cancels, and what you get by moving the rest over, so you're going to have that, and then a piece from there. To the left, you're going to get that bound. OK, then you can multiply with 2 to the power u. This little o1 is really little o1. U is some large constant. So I still get a little o1. And what I'm getting here is a bound, in particular, of 2, 1 minus theta to the power r gamma by 1. Now, like I told you, important thing is that theta is less than a half. So this thing is more than 1. By taking r sufficiently large, I get my gamma arbitrarily small. So to summarize, the basic interpolation step for d equals 2 is the following. So we're having a bound by d2 twiddle delta 1 minus 1 delta 1. Then we move to dp over 2 twiddle with the ball inflation. We interpolate dp over 2 between d2 twiddle and dp with here a decoupling. So a deflation of the size of the interval, and then we are iterating this scheme. Now, the whole story is already here, because the way you should look at it is that the saving we're having here, when we're moving from here to there, so we're replacing delta 1 by delta 1 square. You have an interpolation weight 1 minus theta, so the saving is 2 1 minus theta. So the important thing is that the saving is larger than 1. So the higher dimensional case works pretty much the same, except that this, what I call here the basic interpolation step, becomes considerably more complicated already for d equals 3. And in fact, instead of having a small tree here, this becomes a much larger tree. Now, before I continue, I should remind you what is the Braskamp-Lie multilinear inequality, which is the main tool to get these transversality estimates. So what you have is a collection of k-dimensional subspaces, I going from 1 up to m. M is fixed here, some constant, which satisfy a certain transversality condition, which is written here. And then you have functions gi, which are which say depend on k variables, and you look at gi composed with pi I. So you look at the gi's as functions on these spaces vi. So what happens is that you have a non-trivial bound here which goes beyond Hölder, in the sense that you can bound the, what's that? V, yeah, this transversality condition has to hold for any subspace V over D. So when V is equal to RD, then you get K here and you get K there. So if V's are equal to RD, then it's trivial. If V is a lesser dimensional space, it may not be true. And that requires the VI's to be in a certain appropriate position. In any case, what happens if you are in this situation is that you have a control of, so what you have obviously is a control of the L1 norm of this geometric mean by the geometric mean of the L1 norms. This is just Hölder. But it turns out you can do better. you can get a control not just of the L1 norm of that guy, but of the LD over K norm. So that is not quite enough, but since the time is running out, this has been generalized to the situation where the VI's are not fixed vector spaces, and whatever you get there is called multilinear Kakeya type inequalities. Goes back to a paper by Bennett, Carberry, Tau to prove so-called multilinear restriction results. Certainly we'll not talk about that here. But in any case, these are these multilinear Kakeya inequalities which allow you to prove, together with the wave packet decomposition, my general ball inflation. So when I'm looking at the d twiddle k p over d, delta 1 minus k delta 1, what I can do is increase my ball from delta 1 minus k to delta 1 minus k minus 1. The VI's here are just obtained by looking at the partial Frenet basis on the curve, and because the curve is non-degenerate, if you take enough points, enough arcs, you will make sure that this non-degenerate condition is satisfied. So what is the moral of that? You see, when you take a curve of length delta 1, take its Fourier transform, so this modulus is going to be approximately constant on boxes of size 1 over delta 1, 1 over delta 1 square, etc. But you're also taking the L whatever norm on a ball of radius delta 1 minus k. So eventually what is really happening is that you get something which is constant on boxes which are delta 1 minus k, etc., delta 1 minus k, k times, and delta minus k minus 1, delta minus k minus 2, etc. But because you only look at the ball of radius delta 1 minus k minus 1, it's like you're really having boxes there where you have k small dimensions which are of size delta 1 minus k, and then the rest are going to be large dimensions which are delta 1 minus k minus 1. And basically this is where you would apply Braskamp-Leap, and the k would be exactly the k. The k would be in fact exactly the k which is appearing there. So that is the main inequality in order to, for certain specific moments, get an increment of the ball. So so whatever is written here is just a replacement of the little thing which is here. So we start from d to twiddle delta 1 minus 1 delta 1. This is the same as before. P here is near 12, say, because 12 is the critical exponent for d equals 3. We move to p over 3. There we can, using the ball inflation result, which I just mentioned to you, we can increase the delta minus 1 to delta 1 minus 2. Then we interpolate p over 3 between 2 and 2p over 3. Here, because it's 2, we can do a decoupling. So the delta 1 goes in delta 1 square. Here we apply again, well, we have delta 1 minus 2, but 2p over 3. So we can do again a ball inflation, which is getting 2p over 3, which is getting delta 1 minus 2 becomes delta 1 minus 3. Now 2p over 3, the natural thing to do with that, I don't have time to explain you why, is to interpolate it between 6. You see, you don't want to do the wrong interpolations. So these interpolations, they are kind of optimal in a piecewise linear fashion, right? So somehow when you are here, the right thing to do is to interpolate not between 2, but between 6 and p. If you are at 6, you can use the decoupling result, which is the two-dimensional decoupling result for p equals 6. So that was already obtained just by freezing a certain number of variables, and delta 1, well, delta 1 becomes delta 1 at the power 3 halves, because delta 1 3 halves is just the square root of the reciprocal of that. So we get this interpolation. Now once you are at 6, what you do is interpolating again between 2 and 2p over 3. In 2, you can do a further decoupling and replace delta 1 3 halves by delta 1 at the power 3. In 2p over 3, well, you have the ball inflation principle, which allows you to increase delta 1 minus 3 to delta 1 minus 3 3 halves. And then you are back here, and you repeat. Now, you can tell me, okay, this is an infinite tree, but in fact, you stop at some point, because what's going to happen is that you're going to, how the French, they call it balayage. You're going to push things out to D2 and dPs. And then there is a little weight on other exponents, but anyway, we're just going to majorize these other little weights by dP. And so what we're having is an estimate of D2 twiddle delta 1 minus 1 delta 1, which is an interpolation estimate, where this is basically whatever the P stuff, which we just bound formally. And then here we have the different factors which appear simply by looking at what you're going to have for these different guys here. So you get the delta 1 at various powers. Here there will be integral powers at certain weights. So you get a sum of alpha v plus sum 1 minus alpha v being equal to 1. This is just repercussion. You have all these interpolation weights, right? So when you add the contribution of all the branches, of course, you get 1. But the saving is different. The saving is what you get by looking at these D2s. So here we get a saving, which is going to be 2 times 1 minus theta 1. Here we get a saving, which is going to be 3 times theta 1, 1 minus theta 2, 1 minus psi 2, etc. So the savings, they are going to be, well, you get the exponent alpha v here, which is obtained by taking the corresponding product. The saving is going to be the sum of v alpha v. So you have to see what this sum is. And of course, the sum is going to depend on what are the alpha v's. In other words, what are all these interpolation weights. In fact, there are only 3 interpolation weights here. There is theta 1, there is theta 2, and there is what they call psi 2. But then you have to look at the products. So somehow you have to keep track of that. And the point is that when p is less than 12, this thing is going to be bigger than 1. So that statement is the equivalent of the statement which was here, that this 2 1 minus theta is bigger than 1. And then there is a secondary interpolation. So I will not explain you the general case, but once you have seen the case for 3, that gives you an idea of what is happening in general, except that you get a much more complicated tree with many more powers. But anyway, so in fact, we kept track of it using basically two iterations. There is a way to describe it differently. If you go to Tau's block, there is a way to describe that with what they call Bellman functions, and different explanation of what I'm doing here. But so I believe I gave you some idea of what is happening. Essentially, the whole thing turns on 2 ideas. It is, on one hand, make the interval smaller and smaller using lower dimensional decoupling, and then making balls bigger and bigger by exploiting some kind of transversality. This is essentially what is going on in the argument. So I think I will stop here, perhaps.